Hello and welcome. Today, we are going to pull back the curtain on a brilliant, kind of invisible technology that, no joke, made the entire mobile phone revolution happen. It's called TDMA, and it's the secret sauce that allowed our world to go wireless.
But let's start with a puzzle. Think about it for a second. In any big city, you've got millions of phone calls, texts, and data connections happening all at once. The air should be a complete and total chaotic mess of signals, right? So how does your phone possibly find a clear path to the tower? This was the huge problem engineers had to solve.
And the answer, you know what? It's beautifully simple. It's all about organized turn-taking. Now, I'm not talking about waiting in line at the grocery store. I'm talking about taking turns so ridiculously fast that our brains can't even perceive it. This simple idea, that's the heart of TDMA. So what is TDMA officially? Well, it stands for Time Division Multiple Access. The keywords to latch onto there are share the same frequency channel. See, that frequency, that's the limited resource, like beachfront property. The genius of TDMA isn't about dividing up the property itself, but dividing up time on that property, so everybody gets their own tiny, exclusive moment to talk. Okay, I know that might still sound a little abstract, so let's use a perfect real-world analogy to make this whole thing crystal clear. Just imagine you're in a classroom with only one microphone. To keep things from becoming a total mess, you set a rule. Each student gets exactly 1 minute to speak, and then they have to pass the mic. So student A talks, then B, then C, and once C is done, it goes right back to A. Simple, right? No one talks over anyone else, and everybody gets heard. That, right there, is TDMA in a nutshell. And this breaks it down perfectly. That single, lonely microphone, that's our limited frequency channel. Each student waiting to speak, well, that's a phone user, just like you. And their 1 minute turn, that is their assigned time slot. It's a direct one-to-one comparison. It just makes sense. Okay, so the analogy clicks. Now let's jump from the classroom to the real world and see how this idea gets built into the actual rules that a digital network follows. So in a real network, the system organizes time into something called a frame. Just think of a frame as one full cycle of passing that microphone around the room. Each of these frames is chopped up into a specific number of time slots. If you're on a call, your phone gets assigned, say, slot number 3. That means you use slot 3 in this frame, then slot 3 in the next frame, and so on over and over and over again. And here's the crucial part, the speed. Your phone is actually only transmitting data for a tiny, tiny fraction of a second. It's on, then off, on, then off. But because this cycle, this frame, repeats in milliseconds, we're talking thousands of a second, it creates this perfect illusion of a constant, uninterrupted connection. You never, ever notice the gaps. Now, like pretty much any technology, TDMA has its trade-offs. On the plus side, it's incredibly efficient at packing a ton of users onto a single frequency. And it's pretty flexible. But the downside is a big one. It requires absolutely perfect timing. And if you're not talking, your time slot still exists. It just goes empty. And that's a total waste of capacity. Let's really drill down on that first disadvantage, because it's the most critical part of making TDMA work: synchronization, keeping every single device on the network in perfect time. So let's head back to our classroom for a second. What happens if student B gets a little impatient and starts talking before student A is finished? Or what if they're late and there's just dead air? You get total chaos. In our analogy, you'd have two people just shouting over each other. In a cell network, if your phone transmits too early or too late, its signal literally bleeds into the time slot of the person before or after you. This is called interference, and it would just garble both connections, making them totally useless. The entire network has to act like a single, perfectly synchronized orchestra conductor. All right, let's put this into practice. We're going to do a quick and simple calculation just to see how this whole thing scales up. Okay, so imagine a system where each frame, each cycle of the microphone, remember, has 10 time slots. That means 10 users can share it at once. Now, what if we have 100 users who all need to make a call? How many full cycles or frames does it take for every single person to get a turn? The logic here is pretty straightforward, right? We know one frame can handle 10 users. We have 100 users total. So all we got to do is divide the total number of users by the number of users that can fit into one single frame. And the answer is 10. The system would need to run through 10 full frames to give every single one of those 100 users their turn to talk. It's a really simple but powerful way to scale things up.
It's kind of like a bus with 10 seats needing to make 10 trips to get 100 people where they're going. So, beyond all the technical details, why should we even care about TDMA today? I mean, what is its lasting legacy? Well, TDMA was the absolute backbone of the 2G GSM network. You might not know the name, but this was the technology that let mobile phones go from being a super expensive luxury item to something you could find in everyone's pocket. It's the reason your first cell phone calls were actually clear and not just a bunch of static. It literally paved the way for everything that came after it, from 3G all the way to 5G. All right, time for a quick review question, just to make sure we've got this down. Remember when we talked about one of the key disadvantages? So what happens in the system if it's your turn, your time slot, but you have nothing to send? Maybe you're just listening on a call. That's right. The time slot is just wasted. The network rigidly assigns you that slot, and whether you use it or not, it goes by. No one else can jump in and grab it. And this inefficiency, this wastefulness, is a huge reason why newer, smarter technologies were eventually developed. And now for our final and maybe most important check for understanding. Let's say 5 people are having a conversation on a TDMA network. How many of their phones are actually sending a signal to the tower at the very same instant? Just one. That is the absolute fundamental core principle of time division multiple access. It doesn't matter if there are 5 users or 50. At any given microsecond, only one phone is speaking on that frequency. The true magic of the system is just making that turn-taking so incredibly fast that it feels completely simultaneous to us. It's a perfect illusion. So when you think about it, TDMA was the technology that first taught our devices the art of sharing time. It was a revolutionary step. And that leaves us with a pretty fascinating question for the future. As our world demands more data and faster, how will the networks of tomorrow divide up their resources to keep us all connected? What's the next big idea?